Hello everyone, my name is Pavel. Very excited to be giving a part of our tutorial on Bayesian deep learning here at ECCV. And yeah, in my part of the presentation I'll talk about three different topics. The first one is going to be the connection between Bayesian neural networks and the loss surfaces of neural networks in general. I'll also talk about the methodology of Bayesian deep learning. I'll talk about different methods for approximate inference, some which will be faster but less precise, and also then I'll talk about some more kind of precise approximate inference methods which are not very practical but which allow us to answer interesting questions about the core kind of Bayesian deep learning methodology. And finally I'll talk about some of our recent findings on Bayesian neural networks under distribution shifts and some surprising caveats and limitations that the Bayesian methodology can have in that context. But first, I want to recap some of the motivation behind Bayesian deep learning and explain why I think it's a very interesting topic. So let's consider this example, just a regression problem where we show the data points that we have with red circles, and we want to make predictions at the test input. So, and suppose we have some fairly flexible model like a neural network. So the standard thing to do would be to just train a model on the data. We find a model that is consistent with the training set and which leads to some prediction. And in the kind of classical machine learning, we would just stop here. We would just take this predictive model and we would use it to make our prediction. But in fact, if we retrain the model, we could find a different fit to the data. And it could be similarly good on the training set, similarly valid as a fit to the data. But it leads to quite different predictions on the test input that we have. And we could continue this process and train multiple solutions. And so then the question is, what do we do with them? In other words, there are many ways in which our model could fit the training data. And all of those can be equally good on the train set, but they lead to different predictions and predictions of different quality on the test set. And so in the classical machine learning, we would use the maximum likelihood approach. We would pick the one that's leading to the lowest loss on the training set, But in the Bayesian methodology, we would take a different approach. And specifically, we would consider the so-called posterior distribution. So we would use all of these different predictive functions, and we would average across all of them to get our final prediction. So to be a bit more precise, the posterior distribution in this case is a distribution over the parameters of our neural networks, the theta. And it is a distribution that has a density proportional to the product of the likelihood and the prior. You can think of the likelihood as a measure of how good our predictions are on the training set, how well are we matching the training data. And then the prior is just a measure of how likely we think the parameters are a priori. So before we see any data, would we think that those parameters are reasonable? And more practically, the likelihood is often just the exponent of minus the loss, where the loss is whatever loss function you would use normally for this data. So in this case, maybe a mean squared error loss on the training set. And for the prior, we often use something like a Gaussian distribution, which is equivalent to exponent of minus the squared norm of the parameters with some coefficient. So basically, the likelihood is corresponds to the loss, and the prior corresponds to a regularizer. And we'll talk more about this connection later. And so yes, but we get a distribution. Instead of just optimizing the product of these two things, we get a whole distribution over the parameters. And so yeah, now that we have the distribution, in order to make a prediction, we would use the so-called Bayesian model average. So we take all of the predictions across the entire distribution and we average them to get our final Bayesian model average, the prediction on this test input. So in other words, we integrate over the distribution, we integrate the predictions. And in practice, this integral is intractable. And so instead, we would approximate it with an ensemble. So we would just sample a bunch of neural networks from this posterior predictive distribution, and we would average the predictions across all of them. And so one important thing that I want to emphasize here is that I believe Bayesian inference is especially interesting in the context of flexible models such as neural networks. Because for neural networks, we can get very different predictions for models that are equally good on the training set. So we could fit the training set in many interesting different ways. And that's not the case for simple models such as linear models, where the Bayesian model average doesn't really do anything too interesting. It's still doing something non-trivial, but in the context of Bayesian deep learning, we could actually expect improvements not only in things like uncertainty, but also in the quality of the predictions and the actual accuracy if we do a good job of Bayesian modeling of the parameters. And that's because the neural networks are very flexible and they are under-constrained by the data. So that's equivalent to saying that we could fit the data in many different, non-trivially different ways. So we already started discussing the connection between the loss functions and loss surfaces and the posterior density. But now I want to go a bit deeper into it. So if we include the regularizer into our loss function, then we can think of the posterior density as just proportional to exponent of minus the loss. So any insights that we might have into the loss surfaces or loss functions of the neural networks immediately translate into insights for Bayesian deep learning. And we'll see examples of that later in the talk. And more generally, I believe that understanding the loss surfaces is really exciting and a really important area of research that is important for just understanding deep learning more broadly. And by the way, by loss surfaces, I just mean kind of the geometrical properties of the loss function as a function of the parameters. So kind of the plot, how does the plot of the loss function look like in terms of the parameters of the model. So there are clear connections to optimization. We train our models by minimizing the loss function. And so understanding the properties of this loss function and how it translates to optimization trajectories is really important for understanding deep learning. There are also clear connections to generalization because we have many different optima which may have very good performance on the train set, but translate to different generalization performance. And understanding if there is a connection to kind of the shape of the loss surface, for example, around the optima is really exciting. But for us, the part that we will focus on is a connection to ensembling and connection to Bayesian deep learning. At the same time, the loss surfaces are actually quite hard to study because these are very high dimensional objects. Our models these days have anywhere from millions all the way up to trillions of parameters, and kind of thinking about the geometric properties of a function of a trillion variables is very hard. They're also multimodal and non-convex, meaning that they have many different local optima. They are not just like convex bowl-like shapes. They are in fact very, very complicated functions. And so it's very hard to study them theoretically. And so I'll talk about some work that studies them empirically. And so, yeah, we already started kind of thinking about this picture where we have many different solutions, many different models trained on the same data. So let's go a bit deeper into that and think about it from the loss surface perspective. So in this image, we are showing the loss surface of a ResNet 164 model on CFR100. So a standard image classification model and task. And this model has around 1 million parameters, but here we are taking a slice of the parameter space, and we are looking at just two-dimensional plane that goes through the 3 independently trained models, theta 1, theta 2, and theta 3. And so, to produce this picture, we just train the model 3 times, theta 1, theta 2, theta 3, and then we construct this two-dimensional plane, and we restrict ourselves to this plane, and we plot the loss function at each point of the plane. And then we get this picture. So here, the 3 optima, they are similarly good in terms of both the training performance and also the test performance. They would have roughly the same test accuracy, but at the same time, they are different classifiers. They make different predictions on the test set. They make mistakes on a different subset of the test set. And so we can actually improve our performance by combining them. So we can ensemble them together, average the predictions across the 3 optima, and get a better model. And both in terms of accuracy and also especially in terms of uncertainty, because we are covering kind of more possibilities this way. But also, if we look at this picture, kind of the negative result is that just directly linearly interpolating between the optima, we go into a region of really poor loss. So what this would mean, if this is the case, is that it's actually quite hard to get these really diverse models. If If they are isolated from each other and you cannot travel between them easily, then you need to train from scratch basically every time if you want to get many diverse solutions like this. And that's a very computationally intensive thing to do. And it would also mean that high quality approximate Bayesian inference is challenging, or maybe even nearly impossible, and at least just very, very compute intensive. Because we would need, each time we want to get a new posterior sample, a new kind of point, a new parameter value from the posterior that is different from the previous ones, we would need to train from scratch. And this was the picture that we had in mind for how the loss surfaces, or equivalently the posterior distributions of neural networks look like. For a while, we thought that they have these many different isolated optima or modes, and it's very hard to travel between them. And that seemed kind of hopeless. But in fact, we found that this is maybe not the right way to think about the loss surfaces. And in fact, the optima are not isolated from each other. So here, in each panel of this plot, the bottom two modes, the theta1 and theta2, are the same two independently trained models, resonant 164s, but we are looking into different planes within this million-dimensional parameter space. The first one is what we saw initially with 3 independent modes, but the other two show a mode, what we call a mode connecting tunnel, so like a pathway from one of the modes to the other that never leaves the region of high posterior density. So what this shows you is that we can actually find different subspaces within the parameter space where we can travel between the two independently trained modes while always staying within the region of good solutions. So the posterior, kind of high posterior density is forming a connected set within the parameter space. And it is actually quite easy to find these mode connecting tunnels. They are, we can just do that with a very simple method. And specifically, we directly parameterize a path from one of them to the other. So in this case, we're showing a quadratic Bezier curve that has some parameters, W. The number of parameters of the curve is the same as the number of parameters within the model itself. And then, we can tune those parameters to kind of rotate the curve or find the correct shape for the curve. And then we can define a loss function for the curve. And we just set it to be equal to the expected value of the original loss function for a model that we sample randomly along the curve. So the expectation of a model uniformly sampled along the curve. And when we minimize that loss function, we are ensuring that everywhere along the curve, the loss is low. And we can actually minimize this loss function very easily using gradient descent, using the method called reparameterization trick, which is also quite popular within the Bayesian deep learning variational inference community. But what's important for us here is that this reparameterization trick just allows us to compute the gradients with respect to the parameters of the curve by and we can then use just regular gradient descent or Adam or whatever optimizer to minimize this loss function and fit the curve to the loss surface and find this very simple mode connecting paths. And here we are showing the Bezier curve, but we can also find something as simple as just a polygonal chain with two bands that connects two independently trained modes. And in fact, there was follow-up work that showed that you can find even arbitrary pictures within your loss surface. So you can start with a picture like a skull or a planet, and you can embed it within the loss surface. So for a given neural network, there is a region of the parameter space that such that the posterior density there looks like a cow. Also, if we account for the permutation invariance within the parameterization of the model, so just the fact that you can reorder the neurons in your model or reorder the convolutional filters in your convolutional layers, if we account for that, we can actually get the so-called linear mode connectivity. So we can find that for any two independently trained models, there is actually a linear interpolation between them. they are equivalent to two models that lie within the same local basin of attraction. So to summarize, what this means is that the posteriors are just very rich. Even locally, there is a lot of diversity functionally of the solutions, and it is very fruitful to explore the posteriors even locally, and you can get substantial boosts in performance by ensembling solutions that are near each other, even near each other in the parameter space. And this is just a nicer visualization of this mode connectivity phenomenon. Here it's the same phenomenon where we are connecting two modes, but we plot it in 3D and in much higher resolution. Okay, so now that we have this understanding that the loss surfaces are kind of very rich and very diverse, the very natural idea is, can we just make use of this fact and start exploring the posterior locally, or exploring the region of low loss, and then ensembling the solutions together. And the very simplest thing that we can do is we can just start with a good solution, start with an SGD solution, and then we keep running SGD in order to explore around this solution. So here we are running SGD with a cyclical learning rate schedule. We could also just use a high constant learning rate schedule. So the idea of the cyclical is that we increase the learning rate to make larger steps and explore, and then we decrease it again to convert back to this region of really good solutions. So this way we can really cheaply collect a bunch of weights along the SGD trajectory, and then we can ensemble them together. So and we can do this, and we find that these solutions are good both in terms of their trained performance, but also in terms of their test performance. And we can then ensemble them together and get substantial boosts in accuracy, also in uncertainty quantification, because we are kind of doing this very, very simple, cheap approximation to the Bayesian model average. But in fact, just alongside this work, we found that we can actually do something better in this context. And it is quite, the way we found this was actually by looking at these very pictures. We see that when we run SGD like this, it actually bounces around this region of a very big flat region in the trained loss. But on the tester, actually, the more central points are better within this region. And we can get an even better solution by just averaging the weights of the models that we get from this SGD exploration. And so this is what we call stochastic weight averaging, or SWA. This is a very simple method that just to summarize what it does is we start from a good SGD solution, and then we keep running SGD with the learning rate schedule that encourages exploration, and then we just average the weights that we get along the trajectory. And this way we get just a single value of the weight, so not an ensemble, and this is what we call the SWA solution. And this SWA solution is consistently improving over just normal SGD in terms of the performance. And so one way to think about why it works is by the connection to the Bayesian model average. In fact, you can make an argument that the average, the model with average weights is an approximation of the average of the predictions of the models corresponding to each of those weights. And we can, so in other words, this SWA solution is a very, very simple, very, very cheap approximation to the Bayesian model average. And that's why it's, at least that's a possible explanation for why it's improving performance. And the last thing that I want to mention here is that if you remember this picture that we started with, you could be confused because it looks like averaging the weights is actually not a great idea, because we saw that the interpolation between independently trained models is leading to a very poor model. And that is true. In fact, we cannot average the weights of independently trained models. The reason why it works for SWA is that we are averaging the weights locally. We are not averaging independently trained models. But we have also seen that even locally, there is a lot of interesting structure within the posterior or the loss surface, a lot of diversity in the solutions and the predictions that they correspond to. And so we get a lot of improvement from averaging the weights even locally. And then there are other explanations for why SWA works. For example, it leads to wider solutions in the low surface, which you can argue correspond to more robust solutions. Okay, now let's switch gears a little bit. And next I wanted to talk about methods. So some practical methods for Bayesian deep learning and also just the core methodology of Bayesian neural networks. So first of all, I wanted to discuss SWAG, or stochastic weight averaging Gaussian, which is a very simple extension of SWA, the method that we just discussed, to Bayesian uncertainty estimation. So in the same way as before, we are going to start from a single good SGD solution, but then we'll continue running SGD with a learning rate schedule that encourages exploration, so cyclical or high constant, and we'll collect a bunch of checkpoints along the SGD trajectory. And then instead of just averaging all of them together, we will construct a Gaussian distribution that fits these parameters. And the mean of this Gaussian is going to be the SWA solution. But we'll also have a covariance matrix. And the covariance, we need to approximate it. We cannot do a full scale covariance because it's going to be something like a million by million matrix. So instead we are going to use this low rank plus diagonal format. But what's important is just that we have a distribution over the parameters, and that is going to be our approximation to the posterior distribution. And so then at test time we can treat it as an approximate posterior, and we can do Bayesian model averaging. So we can sample from this distribution and we can average the predictions that we get from the samples. And this way we can improve both the accuracy and uncertainty estimates, even compared to SWA. And so this is a very simple method. It is also quite scalable. So back in 2019, when this paper came out, it was the first Bayesian deep learning method that was successfully applied at ImageNet scale. And it is still fairly popular and applied, especially in the kind of scientific areas and domains such as PDE modeling, astrophysics, cosmology, and rock waves for just improved uncertainty estimates without much additional computation. And just to give a visual intuition for what it does, if you just run SGD with a non-decaying learning rate schedule, it captures the local shape of the posterior or of your loss function. And so SWAG is just trying to capture this distribution of SGD samples. And we find that empirically, if we make plots of the shape of the covariance that SWAG learns and also the shape of the posterior distribution, they match each other. So at least along the directions where the SGD has the most variance, locally SWAG provides a reasonable approximation to the posterior. And practically it improves uncertainty calibration on a range of tasks, meaning that the models produce a better representation of how likely they are to be correct. And so I think SWAG is a nice example of a Bayesian deep learning method, and it is a very simple method, but it's also scalable. It doesn't require a lot of extra compute, and it leads to improved uncertainty. And we'll see more examples of methods like that later in the tutorial, more recent and very successful and practically nice methods. But at the same time, these methods typically don't really allow us to answer fundamental questions about Bayesian inference for neural networks. So for example, SWAG is a very rough approximation to the true posterior. It doesn't really capture the multimodality of the posterior. It is just a Gaussian, very, very local approximation. And while the true posterior is this very complex distribution with many, many modes, with mode connectivity and all of those interesting properties. And so in order to study the properties of true BNNs, we have to use other methods. And so in the next part of the talk, I'll discuss the Hamiltonian Monte Carlo. So Hamiltonian Monte Carlo, or HMC, is a method that is asymptotically exact. What that means is that it's if you run it for a while, eventually it starts actually sampling from the true posterior. And so you can have some guarantees on kind of the quality of the approximations that you get. But at the same time, it's extraordinarily expensive. So we'll see some experiments on CFAR where we had to run an equivalent of 50 million epochs worth of compute in order to get the approximate posterior. And so to cope with these extreme computational requirements for the part of the experiments in this part of the talk, we collaborated with Google Research, and we used up to 500 TPUs for multiple weeks. So we don't have a way of actually reducing these computation requirements. We just had to run it on a lot of compute. But as a result, we did get kind of the first application of high-quality HMC inference to practical neural networks, and we were able to answer some interesting questions, or at least provide new interesting evidence about true Bayesian ends. And so first, let me just quickly recap the intuition for Hamiltonian Monte Carlo. So you can think of it as trying to simulate the dynamics of a particle that kind of slides on the ice that is shaped in the form of your posterior log density. So we start from some position, our current kind of estimate, our previous sample, and then we select a momentum vector randomly. So we just kind of send the particle in some direction with a random speed, and then we simulate the dynamics, kind of simulate the movement of this particle. And you can see that it curves in this case because the shape of the log density is curved. And then in the end, we either accept or reject the sample that we get using something called Metropolis-Hastings rule. And if we accept it, we continue from there and we repeat this procedure. This is our new sample. If we reject, we start over. And yeah, this is a method that is asymptotically exact. It is very well studied and well understood. And it's, in fact, has been used in some early Bayesian neural network work. But at the same time, it is extremely expensive because each step of this simulation of the dynamics, like each dot on the trajectory that I showed, requires a full gradient computation, so an entire epoch over your training set. And you need many, many of those in order to even produce one sample. So it's generally extremely expensive. Okay, but yeah, as I mentioned, we have run it, and we have some interesting results. So first of all, we can study whether or not it actually works, and in terms of mixing, does it actually cover the posterior? And we can study that using the R hat metric. R hat is the ratio of the variances within the chain and between the chains. So what this means is if each chain, each independently run chain of this method is as diverse as a collection of multiple independent chains, then this metric will be close to 1. And otherwise it will be, so for example, if we get stuck in a single optimum, like in a single mode of the posterior very locally, then the different chains will have much higher variance jointly than each one of them has individually, because each one of them is very stuck. And in that case, our R hat metric would be quite large. But if all of them are kind of exploring very effectively, we would get something closer to 1. And in fact, we do see that both in the weight space, when we compute this R hat metric for the individual weights of the model, and also in the function space, when we look at the predictions on individual data points, the R hats are typically very close to 1. So notice that in this plot that I'm showing here, the vertical axis, the y-axis, is logarithmic. So the vast majority of the metrics that we computed is very close to 1. There are still outliers, especially in the weight space. We have some weights for which we don't explore very well. So this method is not perfect, but we are seeing pretty good exploration. So what this means, and also, especially in the prediction space, actually our hats are pretty close to 1, both on CIFAR and on the text classification dataset IMDb. And like geometrically, what this means is that HMC can pass through the mode connecting tunnels. So it doesn't get stuck in a single mode, it keeps exploring and it finds many different modes. So it kind of goes through those mode connecting tunnels that we discussed earlier in the talk. Okay, so now that we've established this method, we can actually use it to answer some questions about Bayesian neural networks. And so the first question here is, do they actually work? So what can we expect from Bayesian neural nets if we are able to run them? And so what we find is that they actually perform quite well. So within the setting that we studied here, Bayesian neural networks are outperforming SGD by a very large margin. And they are actually also outperforming a deep ensemble, so just an ensemble of up to 50 independently trained models of this architecture. And As I mentioned, this is not a statement of like this is a practical method, because HMC is extremely expensive, and even the deep ensembles are like orders of magnitude cheaper than the HMC here. But it is a statement about the properties of the true Bayesian neural network. So the true BNNs are actually interesting. If we are able to run them, they are producing good solutions. And then the next thing that I wanted to discuss is the cold posteriors. So we can introduce this tempered posterior, which is proportional to the regular posterior but raised to a certain power of 1 over t. So if your t, known as temperature, is low, that corresponds to a cold posterior. So the distribution that is kind of concentrated around the high density points of the original posterior. It's a sharper distribution. That's what you see on the right in the plot. Temperature 1 is regular posterior, and temperatures above 1 correspond to kind of less sharp, more dispersed posteriors. And so there was this result that showed that for some settings and some approximate inference methods, actually Bayesian neural networks perform very poorly unless you apply this posterior tempering, and only the cold posteriors are performing well. And this can be viewed as a result that Bayesian neural networks are actually kind of, there is something wrong with them, because the posterior temperature 1 is what Bayesian inference prescribes. But so what we find is that in fact in our setting, if we do the Bayesian inference very carefully with Hamiltonian Monte Carlo, we don't see this cold posterior effect. Actually, at temperature 1, we get the best performance, and we can, by lowering the temperature, we can actually get worse results. And this is quite interesting, and this is saying that at least within our setting, fundamentally there is no issue with the Bayesian inference. Bayesian inference is just working well. And to reconcile these two results, we actually we studied this in a lot of detail, and there was other work from other people as well. But I think one of the issues is that in kind of more practical Bayesian deep learning papers, such as the cold posterior result, people apply data augmentation, and there are challenges with defining data augmentation properly for Bayesian neural networks. If you want to define it very carefully, actually you cannot use it for true Bayesian neural networks, or you have to use it in a very different way from what is done practically. And more broadly, we believe that there are connections between tempering and aleatory uncertainty, so kind of how much you can trust your labels and things like that. And yeah, so there is a very interesting literature on this subject. But fundamentally, I don't believe that there is an issue with Bayesian inference, and even at temperature 1, in the correct setting, Bayesian neural networks can perform quite well. Another question that people often have about Bayesian neural networks is the question of the priors. So you could ask, what should we use as the value of our prior? Because that seems quite important. That is kind of what defines a posterior outside of the likelihood. And we don't have a really great answer for what to use as the prior for neural networks. We don't have an intuition of what the values of the parameters should be independent of the data. But what we find is that actually even very simple Gaussian priors perform well across a wide range of the scales. So we don't even have to set the scale of the prior very carefully in order to get good results. And also we get similar results if we use, for example, a Laplace prior instead of a Gaussian prior, or a range of other priors. And this result is also, I think, consistent with just the general practice of deep learning, where we use weight decay, and it works well. And it is not a very kind of sophisticated regularizer, but it is a very simple thing that works. And for the same reason, I think the priors, Gaussian priors over the parameters, can work well. And you don't need to be extremely careful about setting the prior. And another kind of point I want to make here is that the prior that matters is not just the prior over the parameters in isolation. It is the combination of the prior over the parameters and the functional form of the model. So kind of the architecture of the neural network should also affect, it also affects the prior that you get over functions, over the outputs of your model. And we know that neural networks induce an interesting prior. That's why deep learning works. And so there is no kind of contradiction here. You can get interesting Bayesian deep learning behaviors using very simple priors. And finally, now that we have our HMC samples, we can actually use them to study the quality of other approximate inference methods. So we can compare the predictions that we get from, for example, variation inference or stochastic gradient Markov chain Monte Carlo methods to the kind of golden predictions of HMC. And what we find is that stochastic gradient Monte Carlo methods perform quite well. But one interesting thing is the comparison between variational inference and deep ensembles. So variational inference is one of the more kind of standard methods for approximate inference in deep learning and is often viewed as an example of a Bayesian method, while deep ensembles are often viewed as an example of a non-Bayesian method. But we find that this distinction is kind of quite arbitrary, because deep ensembles are in fact a better, closer approximation to the predictions of HMC than variational inference. So they capture at least some of the properties of the two BNNs that variational inference doesn't. And in fact, I don't think it makes a difference if we call a method Bayesian or not. I think we should just use the methods that work in practice, and we should kind of take the properties that work from Bayesian inference and ignore the properties that don't. Okay. And now in this final part of the talk, I'll discuss a surprising failure mode of Bayesian neural networks, and I'll discuss their behavior on auto-distribution generalization. So in practice, we often hear about the performance of our models on a different distribution compared to the training set. So we might have some distribution of the tasks that we see during training, but then we want the model to perform well on somewhat different tasks at test time. For example, if we train a model for automated diagnosis, we might only have data from one hospital or one collection of hospitals, but we want the models to perform well outside of the distribution on new hospitals, new patients, new conditions, and so on. And similarly for self-driving cars, we might only be able to train them on a finite data set collected in San Francisco, but we want the models and the cars to perform well under new weather conditions, new lighting conditions, when the other drivers are behaving in unusual ways, and so on. So in other words, we want our models to be robust to shifts in the distribution of data. And then the question is, what can we expect out of Bayesian neural networks when the data distribution is shifted? And the kind of intuitive assumption in the community for a while has been that Bayesian neural networks should be quite robust to distribution shifts. And I think the reason for that is that Bayesian neural networks are not just betting everything on a single solution, and instead they are collecting many possible explanations for the data, as we discussed, and they're combining all of them together to get the final predictions. So in a way, they are smoothing the predictions across many different diverse functions that are all consistent with the training data. And that should be robust intuitively. But surprisingly, what we find is that in certain situations, the exact Bayesian neural networks are very susceptible to distribution shifts and much less robust than standard SGD solutions. So here is an example, and this is once again ResNet 18 on CFAR10, and we are comparing the SGD solution to a Bayesian neural network as we increase corruption applied to the images at test time. So we take our regular CFAR10 test set, but we apply this pixelate corruption at different intensity levels. And as we see, when we compare the performance on the original CFAR10 test images, the Bayesian neural network is quite a bit better than SGD. There is a 5% absolute improvement in accuracy. But as we corrupt the images, the performance drops for both SGD and the Bayesian neural network, but it drops sharper, much more kind of drastically for the Bayesian neural network. And at the highest degree of corruption, there is a 25% decrease in performance in the Bayesian neural network compared to the SGD solution. So the performance drops from 65 to 40%. And that's pretty surprising, especially given that the Bayesian neural network here is a huge ensemble of thousands of samples, and it took multiple weeks on 500 TPUs to get those samples. And at the same time, the SGD is just a regular model trained very fast without any tricks for improving robustness. So what's going on here? And now we have a pretty good intuition actually for why this happens, and I'll try to explain it next. So suppose we do this on MNIST, and suppose, just for simplicity, we have a fully connected neural network, and we'll generalize to convolutional networks afterwards. So MNIST has a bunch of pixels that are just always black, and let's say that black is represented with zeros, again for simplicity. So we have a bunch of inputs to our neural network that are just always zero. And then if we think about the weights that connect to those inputs in the first layer of the model, those weights will always be multiplied by zero on the training data. So their specific value does not matter at all for the predictions on any of the training data, and it doesn't affect the likelihood. So yeah, if we think about the posterior distribution, recall that it is proportional to the product of the likelihood and the prior. And the likelihood will be constant with respect to the values of those weights, because once again, they're just always multiplied by zero on the training data. And so, in other words, the posterior will just be proportional to the prior distribution density. And effectively, we will be sampling those weights from the prior. And that is what we see in practice when we look at our HMC samples. If we consider the weights that are corresponding to the corner pixels of the image, they are just random. They're just drawn from the prior, and there is no structure. And on the other hand, for the SGD solution, we see a lot more structure. And in particular, the weights around the corners of the image are set to approximately zero. And the reason for that is that, once again, those weights have no effect on the predictions of the model. But the SGD, instead of sampling from this posterior distribution, it is maximizing the density. The other way to refer to the SGD solution here is MAP, maximum a posteriori. It's just maximizing the posterior log density, or equivalently minimizing the loss with the regularizer. And that regularizer, or prior, is forcing the SGD to set those weights to zero. Like weight decay, for example, pushes the weights towards zero. And so then, at test time, if we perturb the input, so we apply, for example, some noise, let's say Gaussian noise, to the image, then those pixels that were always black will now sometimes activate. And effectively, in the Bayesian neural network, we'll take those random values of the pixels and we'll multiply them by the random weights that are sampled from the prior. We'll propagate that to the next layers of the model, resulting in significant changes in the predictions. And also, those don't cancel out across multiple samples because the model is nonlinear, so it actually leads to a shift in the expected predictions of the Bayesian neural network, not just in the uncertainty. And on the other hand, for the SGD solution, it will just ignore those perturbations because the corresponding weights are set to zero. And this is the main intuition. We can actually formalize it and generalize it quite a bit. So here's an informal statement of a theorem that we prove. So suppose we have an ID Gaussian prior over the parameters in the fully connected Bayesian neural network, and suppose there exists any constant linear combination of the input features in the data. So what we mean by that is that the data lies in some affine subspace of the parameter space. So it lies in some hyperplane. It doesn't span the entire input space. And so it doesn't have to be that pixels. It can just be that the data kind of doesn't span the whole space. And that is the case for almost all of the practical datasets that we can work with. So if that is the case, then there will exist a direction in the parameter space of the model that corresponds to this constant direction in the feature space, in the input space. And along this direction, the posterior distribution will just coincide with the prior. And on the other hand, the SGD solution will set the weights along that direction to zero. And if we perturb the data and break this correlation between the features, we kind of take the data outside of the affine subspace that it lived in, then the SGD solution will ignore the perturbation, but the Bayesian neural network will actually be very susceptible to this perturbation. It will, the predictions will change significantly, and it will lead to a degradation in performance potentially. We can also generalize this to convolutions in a very simple way. So we can consider the data set of all the patches in the images that interact with the convolutional filters in the first layer of the model. So let's say all of the 5x5 patches in the input images. And then if there are a constant direction in those, in the dataset of all of those patches, then we'll have the same issue. There will be, the Bayesian neural networks will set the corresponding weights to the prior, samples from the prior, and if we break this correlation and we take the data outside of the subspace, then the Bayesian neural network will degrade significantly in its performance. And actually, on both CFAR and ImageNet, if we consider, for example, 5x5 patches, there are certain directions that are approximately constant. For example, these checkerboard patterns that I show here are all very low variance directions in the space of patches. We almost never see these like checkerboard patterns in the real data. And if we apply Gaussian noise, we can shift towards seeing some of those checkerboard patterns, and the Bayesian neural network predictions will degrade significantly. But again, SGD will just ignore that because the corresponding weights, the projections of the weights on those directions will be very small. And we can also empirically see that indeed, if we consider the directions of high variability in the data, so the first few PCA components, then both SGD and the Bayesian neural network have kind of similarly high variance in the weights, so similarly high kind of degree or magnitude of the weights. But for the last few PCA components, so the directions where the data has almost no variation, is almost constant, the SGD weights are just zero. They just ignore those directions. And on the other hand, the Bayesian neural network, the magnitude of the weights is the same as the prior. So if we project the weights on those directions, it's the same as projecting samples from the prior. And also, if we perturb the data along the first 50 PCA components, so along the directions where there was high variability in the data to begin with, then we see very similar performance between the BN and the SGD solution. So we use map here to refer to the SGD solution, that's maximum a posteriori. So again, when we perturb the data along the high variance directions, we don't see this difference between SGD and the Bayesian neural nets. But when we perturb it along the last 50 PCA directions, so the directions where the data is almost constant, then SGD just is flat, the performance is flat, the model doesn't notice that we perturb the data. But the Bayesian neural network, the performance drops a lot, and we see this huge difference in robustness. And yeah, this is the main intuition, and this also immediately gives us an idea for how we can try to fix this issue. And specifically, we can just introduce a prior that has a low variance along the directions that corresponds to low variance directions in the data. So we can just compute the empirical covariance matrix of our input data, like input images, for example. And we can use that as the covariance matrix for a Gaussian prior for the first layer in the Bayesian neural network. All of the other layers can use the standard prior. So this issue is specifically with the first layer. And yeah, we can also generalize this prior to the convolutional neural networks pretty easily. And empirically what this does is, for the case of MNIST that I described, we'll just have very low variance prior for the weights that connect to those dead pixels. And so the posterior will also be very low variance, and approximately the samples will just be approximately zero. And when we multiply the samples by from the posterior by the random input pixels, we'll just get zero again. So they will not affect the predictions. And in fact, this simple modification to the prior largely fixes this issue with robustness, and we get much better performance under distribution shifts and corruptions to the input images when we use this prior compared to the standard prior. Okay, so this is the end of my talk. I have a few takeaways for you. So first of all, I think Bayesian neural networks are very interesting, and Bayesian inference is especially interesting for flexible models such as neural networks. So models where we are constrained by the data, under constrained by the data, where we can fit the data in many different ways, and all of those ways would be equally good, but we cannot select any one of them. And also, I believe the low surface analysis can provide useful insights about both standard training, and we have the ideas like stochastic weight averaging, but also for ensembling and Bayesian inference. And I think the insights such as mode connectivity are very encouraging for Bayesian deep learning. And also, Bayesian neural networks, if we perform approximate inference very carefully, can perform well, and we don't see issues such as the cold posterior effect or such as very high dependence on the specific details of the priors. They just work pretty well. But of course, the caveat is that the approximate inference is challenging and it can be hard to get good performance. And also there are surprising failure modes, such as this auto-distribution behavior that we described. It is quite surprising, and we cannot expect Bayesian neural networks to just always be better than SGD. And I think more generally, Bayesian neural networks are just very interesting models, and there are useful insights. Even if I don't think that we should be doing exact Bayesian inference for modern, very large-scale deep learning, we should. I think there are still very useful intuitions that we can take out of Bayesian inference, and Bayesian-inspired methods, for example, for improved uncertainty calibration and just improved predictions. And we'll present more of those methods in other parts of this tutorial today. And finally, this work is done in collaboration with many amazing co-authors. So my advisor Andrew, Sana, Wesley, Patrick, Sanyam, Matt Hoffman, Sharat Vikram, Dmitry Vetrov, Tim Margaripov, and Dmitry Bedobrikhin. Thank you so much.